Hello, my name is Robin Jackman, and today we'll be talking about Interference 101. Today's presentation will cover a number of areas. First, a short section on radio system definitions, a second section on interference definitions, and a third section on measuring and locating interference. In order for us to fully understand interference in radio networks, we first have to understand a simple definition of what's in a radio network. This slide shows us simplex radio, basically a small system where we transmit and receive on the same frequency. In this slide, it's easy to see that the radio horizon for each of these mobiles changes. Those mobiles that are higher can see further distances, while those mobiles that are not as high can be blocked and their communication will not be heard by other mobiles. In order to alleviate the problems with simplex radio repeaters were invented. With the radio repeater, the radio horizon is now based on the repeater system itself. So those mobiles in the further ranges can effectively have further coverage provided by the repeater itself. The repeater, in essence, simultaneously retransmits all the information that's on the input channel to the output channel. The simplified block diagram is shown here on this slide. Essentially, we have one transmit channel, one receive channel, and a duplexer, which is a filter that allows the simultaneous transmission and reception over a common antenna. Modern radio repeaters are quite a bit different than the simplified block diagram shown in the previous slide. Here we can see where we have diversified receive and transmit antennas, as well as a receive multicoupler. In this instance, or example, it's much more complex for us to describe the full operation of the radio repeater. There are many interconnects and different paths for the radio frequency to follow. Trunked radio systems are a network of repeaters spread out over a larger geographical areas. Trunk radio systems were invented so that we can get more efficient use of the frequency pairs used in each repeaters. In general, what we have in trunk radio systems is large groups of operators or operations separated into distinct talk groups. Each time a user in a specific talk group requests a channel, the system will automatically dedicate one repeater pair for that talk group. The interesting thing is that the talk group itself could be separated over a large specific area, like a state or even a country. There are different types of trunk radio systems in the market today, including P25, NXDN, Tetra, and DMR type systems. Basic cell systems are essentially a network of repeaters. There is some technology or terminology that we have to get used to. In general, the uplink is described as communications between the mobile to the BTS, or the base station transceiver system. The downlink is defined as the BTS to mobile communications. The tricky bit with cellular systems is that we have co-channel frequency assignments by design. Each cell can actually reuse the same frequency pair. Examples of the cellular system in use today include GSM, 3G, LTE, or so-called 4G systems. Modern cellular systems are somewhat different than traditional repeaters insofar as the complete repeater system is encapsulated within the antenna itself, meaning we have less cables connecting the ground system to the antenna system. By definition, a lot of these systems are called air cells, whereby we only have fiber going up the tower to control and power the radio transceiver system on top of the tower. Distributed antenna systems, or DAS systems, are very common today. They're used to improve the coverage inside large buildings or even stadiums. They can be passive or active, but they have in common the theory that they retransmit signals from the outside of the building to the inside of the building. This slide shows us the block diagram of a distributed antenna system for a large stadium. It's easy to see by the block diagram how we can have separate zones inside the actual building itself. What makes it more complex is that each of these can be considered a wideband transceiver. In summary, radio is more popular today than it ever has been before. There are many different types of radio systems in use with many different types of customers. In order for us to learn about radio and to learn about the effects of radio, one must understand the interference and quality of service issues that affect these different types of systems. In the next section, we'll discuss the interference definitions themselves. So when we discuss interference, the question is, where do we begin? First, we need to understand our own radio system. Second, and probably more importantly, we need to have situational awareness. Who or what other types of systems are around us? Are we a part of an antenna farm or not? When does the interference actually happen? When the interference does happen, how does it actually affect the system operation? These questions have to be answered before we can determine what type of interference is affecting us. Co-channel interference is probably fundamentally the most simple type of interference we find today. Essentially, we have more than one transmitter on the same frequency. In general, no one owns a frequency. Globally speaking, every frequency we use today is used by someone else. When we think of co-channel interference, what we're really discussing is noise or energy on our received channel. Adjacent channel interference is somewhat more complex. Essentially, adjacent channel interference is any energy that's coming from off channel. It's the overlap area or the contribution from the adjacent source that causes problems in the victim receiver. Essentially, what we normally see is some form of desensitization or blocking of the victim receiver. This manifests itself in a smaller coverage area. The challenge for us here is we can't forget the effects of propagation. Depending on the frequency range we are in, the source of this adjacent channel interference could be very close by or very far away. When we start considering co-channel or adjacent channel interference, one must understand how a RX preselector works in modern radio transceivers. Essentially, today, transceivers are designed to operate over a wider frequency range or multiple channels. That means that the preselector inside the radio is necessarily wide as well. If any energy, whether it be on channel or adjacent channel, falls within the preselected band of the receiver, it will affect the quality of the receiver, meaning any uncorrelated energy within the receiver passband will cause a desensitization issue. Essentially, we have an off-channel source and an on-channel problem. When considering the source of interference, we have to consider what frequency range we're operating in. In general, if we think of HF, VHF, and UHF spectrum, we have different propagation characteristics for each frequency range. By physics, the HF, or 3 to 30 megahertz frequency range, can have sources of interference propagate from much further distances compared to VHF or UHF communications. In general, VHF communications are line of sight, or line of sight plus 30%, which we call the radio horizon. UHF, however, has a much shorter propagation characteristics. The rule of thumb that we typically apply is that each time we double our frequency range, we halve our propagation distance. Intermodulation interference is probably one of the most complex sources of interference that we have today. The challenge with intermodulation interference is that we have two or more signals that mix together to create other products, and these other products can land on victim receivers. We call this mixing intermodulation, or intermod by short. By far, third-order intermodulation products are the most popular. In the example on this slide, we can see that 2 times transmitter B minus transmitter A results in a signal at the victim receiver at 157 megahertz. The challenge here is that we can have receiver-generated intermod as well as transmitter-generated intermod. The active components in each type of these systems can provide the location for the mixing to actually occur. This slide shows where the products can occur from mixing between transmitters A and transmitters B. In the previous slide, we showed that the third order intermod project was the most popular, but it's by no means the only one. Fifth, seventh, and ninth order products are also possible. When it comes to intermodulation interference, there are some common connectors or common components in modern radio systems that we can look at. Coaxial connectors, RF feed lines, in general, interconnection issues between cables are a primary area of concern when we think about intermodulation interference. Also included in that is antenna problems themselves. Remember that all of these components are exposed in the environment and can age varyingly. Impulse noise is defined as man-made interference. And essentially what we mean by this is that it's RF interference that's coming from some sort of mechanical or electronic device that is man-made. In general, it's broadbanded, meaning it will cover sometimes hundreds of kilohertz or even tens of megahertz of spectrum. The difficulty with impulse noise is probability of intercept. Impulse noise is typically very fast, and when we try to measure impulse noise, slow sweeping spectrum analyzers aren't able to fully characterize what the noise signature looks like. Common sources of impulse noise can be found in the industrial space, commercial bakeries, welding, compressors, even large power supplies for neon signs. Impulse noise can actually happen and be the result of data, meaning we could have a distributed antenna system that goes into some form of compression and becomes a noise generator. Another common source of impulse noise is high power electricity transmission systems, motors, power distribution, even transformer stations. The biggest challenge for us when we're solving interference is finding a tool that can mimic the sensitivity of the victim receiver. If we consider a modern LTE transceiver, it's not uncommon for us to see sensitivities on the order of minus 120 dBm. The challenge for us is to select a piece of equipment, in this case a spectrum analyzer, and set up the spectrum analyzer so that it has the same sensitivity of the victim receiver so that we can see the problems or the noise or the interference that's affecting that victim receiver. The key challenge there is that very often when we set up a narrow resolution bandwidth span or setup, is that the speed of the spectrum analyzer suffers greatly, meaning the probability of interference, or the probability of intercept, meaning how much or how fast can we actually measure the spectrum, can be degraded by the narrow resolution bandwidth filter setting. DPX spectrum measurements allow us to improve the probability of intercept. That means we can see shorter transients that might be affecting the victim receiver. The question we have to answer is how fast is our spectrum analyzer capturing data? Do we actually know what the probability of intercept is? Can we specify or can we measure what the speed of our spectrum analyzer is and determine what the minimum signal duration has to be in order for us to guarantee that we're going to see the interfering signal? DPX spectrum allows us to look at an RF persistence display. It's still low frequency on the left and high frequency on the right, but for each pixel in the display there's a counter. Every time we measure energy at that pixel, we increment the counter and then colorize that pixel based on the hit count. So essentially it's power spectral density over time that we're looking at. We get to look at signal occupancy, finding out how often a signal is actually present. And this is key for solving interference. In this slide, we have the exact same setup as we previously showed. This is an LTE downlink, but using DPX spectrum measurements, it's easy for us to determine what radio resource blocks are actually being used. DPX spectrum measurements, or persistence RF measurements, aren't enough to show us how interference is affecting the system because they don't tell us how often things are happening. That's where DPXograms or spectrograms come into play. They show us power spectral density over time. In this case, real-time power spectral density over time. With this display, we can see how often a signal is happening and actually do a carrier correlation to determine how an intermod is actually occurring or when the intermod is actually occurring. When we're looking at spectrograms or DPXograms, the key feature beyond the ability to record the spectrum over time is also the ability for us to see into the noise floor, looking for non-randomness in the noise floor. Non-random events are typically man-made. So with spectrograms, we can more accurately determine what the power spectral density is over time. Once we have determined what the interference mechanism is, the key feature now is to find out how often it's actually occurring so that we can determine where the source of interference actually is coming from. When we think of frequency mask triggers, this feature allows us to essentially create a shield around the victim receiver, and when we detect activity, automatically record a screenshot or even record the RF so that we can figure out how often the problem is happening. As odd as it sounds, demodulating even an LTE signal is actually quite useful when we start trying to figure out where the interfering signal is coming from. Each digital emission actually has a fairly unique sound when we put it through an FM demodulator. So listening to an interfering signal can help us determine what the source might actually be. When it comes to actually determining the location of the source of interference, it can be quite complex. We need tools to help us sift through the mountain of data to try to determine where that source of interference is coming from. In modern spectrum analyzers, we have the ability to use distance and time triggers to collect information automatically. With this information, we can actually create a heat map which helps us localize the source of the interfering signal. This is a lot safer and sometimes a lot faster than classic direction finding techniques because we can collect a lot of this data much more simply and then put it through a tool like Google Earth in order to map it for us. As we're moving around attempting to identify the source of the interfering signal, it's very useful for us to be able to instantaneously capture all of the information about received signal strength indication, spectrum, DPX, and lat and long information automatically. In this example here, the Map It toolbar provides a simplified interface to collect all of that information instantaneously. While collecting this georeference data, Tektronix also provides the means to numerically export all of this data as a spreadsheet. This data itself can then be merged into your own georeference system or exported to third-party applications. This slide shows mapping the generic data with a third-party tool, in this case Google Earth. It's a very simple matter for us to use the Google tools to import the data from the georeference measurement system. In any interference system, having a quick and easy way for remote desktop control is very important. The Tektronix Signal View application, combined with our disaggregated USB spectrum analyzers, is a very simple platform for remote desktop control with popular remote desktop programs. Locating interference. Ultimately, we have to figure out where is the interference coming from. The most important thing that we can have is situational awareness. Knowledge of our frequency, modulation, duration, crest factor, sound, also observing time of day, what the weather conditions are, even the time of year. All of these factors have to be used when we're determining the source of interference. One of the most common questions that we get is, well, what type of antenna should I use when I start measuring interference? It's a much more complicated answer for this question because we have to understand the different types of antennas that people use today. In this slide here, we're talking or looking at the coverage pattern of a basic dipole antenna. And essentially, this shows us what the transmit and receive pattern for this type of antenna would be. In this example, we can see that it's not directional, but rather omnidirectional. So there is no directivity when we're using a dipole antenna. This type of antenna is, however, very useful as we get closer and closer to the source of interference. While it may not be directive, it has a good all-round antenna pattern. By comparison, a monopole antenna, or in this case a rubber duck, has a much different antenna pattern compared to a dipole. We have to understand that it essentially has half the antenna pattern as the dipole does. Curiously enough, while the horizontal antenna pattern is quite uniform, the elevated or vertical antenna pattern has a big null in the very center of it. This means that we can actually use this type of antenna for what I would call inverse direction finding, meaning we go for the null in the signal and not the peak of the signal. These types of antennas are both very useful as we get closer and closer to the source of interference. It's very common for us to use these types of antennas as we get within what I would call visual range of the source of interference. These antennas combined with the use of an attenuator allow us to essentially zero in on the location of the actual transmitter itself. The technique basically is to start adding attenuation as you get closer and closer to the source of energy. While this might not sound logical, what we're really doing is exploiting the sensitivity of the spectrum analyzer. Remember, as we get closer to the source, the amplitude of the signal or the amplitude of the interference is going to increase. As we start adding attenuation, we'll be attenuating the clutter or the adjacent channel spectrum around us. And as you get closer physically to the emitter, we will be able to see it with our spectrum analyzer because our spectrum analyzer is very, very sensitive, even with all of that attenuation on the input. Common today in the industry are what we call multi-band log periodic antennas. These antennas cover a very, very broad frequency range from VHF to high UHF. This slide shows us here what the antenna radiation and reception pattern is for a common log periodic antenna. You can notice that it is quite directive. However, it's not as directive as, let's say, a Yagi antenna. The reason why this is important, as we're using this type of antenna for direction finding, one must understand that to get a good peak out of the signal actually takes quite a bit of skill. The front to back ratio also must be taken into account. As you start peaking the signal or looking for peak signal amplitude, it's important for the operator to go 180 degrees behind him or in the opposite direction to determine if the signal is actually coming from the opposite direction. This is due to the fact that we may have a 10, 20, 30 dB front to back ratio, and sometimes you might be pointing in the opposite direction. Note that as you get closer and closer to the target emitter, these types of antennas lose their efficiency, and it's more accurate and more efficient to use an antenna with less gain or less directivity. By comparison, a Yagi antenna is much more direct. It has a greater front to back ratio and a much more narrow beam width. The trade-off is much more narrow frequency range. So when we think about using a multi-band log periodic versus a Yagi antenna, the multi-band log periodic will be able to operate over a much broader frequency range. It's not uncommon for it to be able to operate over hundreds of megahertz. A Yagi antenna, by comparison, may only be able to operate over 50 to 100 megahertz. But the directivity of the Yagi antenna is much better, meaning we get a much more sharper peak when we start using it for direction finding purposes. When we start considering triangulation, the basic theory is we need to have two good measurements of a signal from two diverse locations. Theoretically, when we plot those two bearings on a map, the intersection point would indicate where the source of interference was coming from. The challenge for us today is that as we do direction finding in any dense urban environment, our measurements are going to be drastically affected by multipath interference. It's really important for us to be able to keep moving and to collect as many measurements as possible to improve the accuracy of the direction finding operation. One other consideration is that very often we're doing our direction finding at ground level. Remember that the victim receiver may be on the top of a building. That means that the radio horizon of the victim receiver is dramatically different than the radio horizon for us where it's on the ground. In general, when I start talking about this type of direction finding technique, it works best when we are far outside the area of operation of the victim receiver. So we have to be on the outside of the problem looking in. If we're inside the target zone of the receiver, trying to use a multiband log periodic in a dense urban environment with a lot of multipath, we won't get a lot of good results. It's more important or probably more accurate for us to collect multiple data points from outside of the target area to build up the population of measurements to improve the accuracy of the direction finding operation. When we're physically located on the ground with our spectrum analyzer and antenna, we need to keep track of several things. I like to keep track of received signal strength indication, meaning I'm measuring the received level of the interfering signal. It's also important to have your DPX spectrum or your persistence spectrum running at the same time because we need to determine how often we're seeing the signal and if we're seeing the right signal. This is a big problem when we have dense urban environments where we have multiple frequency assignments. It's much more difficult to determine what type of frequency we're looking at or what type of spectrum we're looking at if the only thing we're looking at is a basic spectrum display. The DPX spectrum or RF persistence spectrum is going to give us an idea whether we're looking at a co-channel problem or an interstitial problem, and if we're measuring the right problem at the right time. As you start collecting bearings, the most important thing is bearing population and signal strength. As we start laying bearings down on a map, we essentially end up with an area of uncertainty. Given the number of bearings and the signal strength we're working with, the area of uncertainty may be larger or smaller. Most important is that the area of uncertainty is not an exact science. What we really need to do is find a general or generalize the area where the interference is coming from so that we can get closer and get on the ground and determine what the source of interference actually is. When dealing with direction finding antennas in general, we have to be very careful with the type of antenna that we're using, as well as what kind of active components might be in the antenna itself. In this example here, we actually have an antenna with 3 different preamplifiers built into the instrument or into the antenna. It's important for us to be able to turn the preamplifiers on and off, particularly if we're in a dense urban environment, because very often there's so much RF energy in these environments, the antenna amplifiers themselves can be easily overloaded. Once we're inside the area of uncertainty, or we think we may be close to the target source of interference, it's actually important that we use non-active antennas in our work. As you get closer to the emitter, depending on the power of the emitter, active antennas can be easily overloaded, and this will cause a great amount of trouble as we're trying to determine the source of energy. This slide shows us a real-world example of using a real-time spectrum analyzer to determine when interference was actually happening. In this case, we were measuring the output of an antenna farm that had a spurious transmitter. The trouble with this spurious transmitter is that the requirements or the effects or the factors that caused the spurious output were transient in nature, and the victim receiver was over 3 megahertz away. So it was important when monitoring this problem to see not only a wide span, but also high resolution measurements over a long period of time, which clearly showed when the spurious component was actually occurring. In this example, we can do a visual carrier correlation to determine that when all 4 emitters were on simultaneously, there was a complex mix which resulted in a spurious component affecting our victim receiver. Interference work is difficult. When we're trying to solve an interference problem, we need to have situational awareness. First, you need to understand our system. Is it a simplex operation, duplex operation, wide area, narrow area? What type of radio system are we dealing with? We also need to understand our spectrum. HF, VHF, UHF. Is it a co-channel system? Is it a non-co-channel system? Are there other systems nearby or sharing the same tower that are causing our issues? Third, we need to understand our interference. What is the spectrum signature of this interference? How often is the interference happening? What is the effect of the interference on the victim receiver? In order for us to solve the problem, we have to understand all of these issues. Your time is important. Thank you for investing some time with us today to understand interference in wireless networks.